All right, guys, let's tackle this next lesson, 10-5 on tangents. We're going to learn what tangents are. Then we're going to solve some circle problems using properties of tangents. And in our last lesson, which was about inscribed angles, we worked with inscribed polygons. Tangents, we're going to see when we see the definition of a tangent, you're going to understand why we're now going to use them to solve problems involving circumscribed polygons around the outside of a circle. So let's jump into our new vocabulary here. We have, first of all, what is a tangent? Okay, well, if I have a circle and I pick a random line anywhere, there's three possibilities. That line may not touch the circle at all. It may not intersect it anywhere, or it might intersect that circle in two locations. But there's a third possibility. Maybe that line just barely brushes the circle and touches it or intersects it at just one point. The only way this can happen is if this line is what we call a tangent. Okay, so a tangent is going to just barely touch and intersect a circle at one point, and we call that point, that is our point of tangency. Okay, so we also are going to look at a couple other terms here. Common tangent. If we're dealing with more than one circle, could we have tangents or lines that are tangent to both of those circles or multiple circles? And then we're going to talk about circumscribed polygons, which are, you remember from our last lesson, we had inscribed polygons. They were inside the circle. And with tangents, what we can do is if these lines are just brushing the circle, then we can have what are called circumscribed polygons. Circum meaning around, going around. Okay, so this would be, this guy here is our circumscribed polygon. So we're going to work with those. All right, let's start with circle theorem 10. This is basically our definition of tangency when it comes to circles. For a circle and a line that lie in the same plane, the line is tangent to the circle if and only if it is perpendicular to a radius drawn to the point of tangency. Okay, so you can kind of picture this. If I had one of those other conditions, where I was either not intersecting the circle at all or I was intersecting in two places, then I wouldn't be able to be 90 degrees to this radius. But if I am just touching it at one point, the only way that can happen is if this is a right angle. If I pick that point and I draw back to the center, I must create a right angle, because if I were not 90 degrees, if I were a little bit this way or a little bit that way, you can start to see now I'm going to intersect the circle in two locations, even though it's going to be very, very difficult to see. If I'm not 90 degrees, if I'm just slightly not 90, you can see what's going to happen is I'm actually crossing in two locations and I'm not a tangent. All right, before we jump into our first example, I know what you're thinking, Mr. Rogers. Why do they use in math this term tangent to mean two different things? Isn't it confusing? Shouldn't everything unique in math have its own definition and have its own term? Well, in fact, this word tangent that we learned in trigonometry, our tangent function, right? Tangent of some angle theta equals opposite over hypotenuse. Remember that? Oh, no, excuse me, opposite over adjacent. Gotta watch me here. Opposite over adjacent, from which we get TOA, right? The opposite over the adjacent side, TOA. Okay, why do we use that word tangent? And now when we're talking about circles, we're using the tangent too. Well, next year in Algebra 2, and maybe in pre-calc, definitely in pre-calc, you're going to run into something called the unit circle, okay? And basically it puts our trig functions on a circle with a radius of 1, because it makes it really easy to pick any old coordinate x comma y and work with it and relate this angle that it creates. Okay, I'm going to give you the Cliff's Notes version of this just so that you can see that this word tangent that we use in trigonometry and the word tangent that we use in circles are pretty closely related. This is the unit circle that you're going to see in Algebra 1 and Pre-Calc. What you're going to want to do when you get into Pre-Calc is ask for Mr. Rogers' augmented unit circle, where we expand and we continue our trig functions outside of the circle. And if we keep going, here's what happens. This line right here, this line represents the tangent of this angle theta, because it is opposite over adjacent. And since the adjacent side is 1, it's a unit circle, a radius of 1, then if we said the tangent of theta equals this over this, and this is 1, then this side must be the tangent of theta. And you'll notice that is the point where this line comes down and just touches the unit circle at the point of tangency. So that's where our word tangent comes from, and that's why these words are actually related. They're not two completely different words that mean completely different things. Okay, now here they want us to draw all of the tangents common to the circles in these diagrams. Okay, so common tangents mean they're going to be tangent to both of our circles. So here, here. Can we draw common tangents to these two circles in diagram 1? In this particular case, I can't draw any common tangents, can I? I mean, I could try to draw any line that I try to draw just barely tangent to the outside circle, obviously is not going to intersect the inner circle at all. And any tangent I attempt to draw on the inner circle must necessarily intersect the outer circle twice. So this guy, no common tangents. Okay. How about for diagram 2, these two circles? How many common tangents could we draw between these two circles? Well, in this case, we could just barely brush the edge of both of these circles and draw a tangent there. And if you were to connect the center of this circle to the point of tangency, that'd be 90 degrees. And the center of this circle to its point of tangency would also be 90 degrees. So there's one common tangent, but we can also draw one over here, can't we? Absolutely. Look at that. And so here we have two common tangents. How many common tangents could we draw for these circles here in diagram 3? Well, we could kind of do this idea again, right? We'll pick up one tangent, and we'll pick up another tangent up here. Get a little closer there. Hopefully that's good. So 2 common tangents. Are there any others? Could I thread the needle like this? Right? I can do that. I could go tangent above this one and tangent below that one. There's another common tangent. Yeah, I could do the same thing here, right? We could just hit the top of this one and hit the bottom of this one. See if I can get it a little better this time. All right, so how many common tangents do we have here? Here we have 4 common tangents. Let's do one more of those. How many common tangents could we draw to these two circles here? Let's just see what we got here. I could do this one, right? No problem. Yep, I like that. And we can do this one. This guy looks pretty good. Are there any other common tangents? Turns out that if I were to connect the center of this circle to the center of this circle, and then turn a 90-degree angle, I could pass one more common tangent right between the two of them. It's almost like these two circles are just kissing one another, just at that one point of tangency. They actually share their point of tangency with each other and with this one common tangent that splits in between them. All right, let's try this one. Is segment AB tangent to circle C? Well, how could we tell? Our definition of tangents say that if a segment is tangent to a circle, then it is going to be perpendicular to a radius at the point of tangency. So this would have to be true, wouldn't it? If AB is tangent to this circle, then that's got to be a 90-degree angle. How could I figure out if that's a 90-degree angle? Well, we could use our Pythagorean theorem, right? Could we go ahead and test and see if in fact a squared plus b squared equals c squared? Or I should say, the way I labeled this triangle, c squared plus a squared equals b squared. Is that true? 30 squared plus 16 squared equals 34 squared. Is this going to be true? Let's test it. 30 squared is 900. 16 squared is 256. 34 squared is what? 1,156. And when we add these two together, you can see. Now, what can we declare about this triangle when we find that this is a true equation? When a squared plus b squared equals c squared, then we know we have a right triangle. And if this is a right angle, what can we say about AB? AB is tangent to the circle. How about here? Is AB tangent to circle C? Could we go ahead and test this again? Could we say, is 59 squared plus 32 squared equal to 70 squared? Let's test that. All right, off the top of my head, I don't know 59 squared. Maybe I should. I get 3,481 plus 32 squared. I feel like I should know that. Is that like 1,024? Yeah, it is. 1,024 equals 70 squared is 4,900. Okay, 3,481 plus 1,024 gives me 4,505. Okay, oops. Now you'll notice here that is not true. So if a squared plus b squared does not equal c squared, then guess what? Not 90 degrees. Is AB tangent to circle C? No. All right, here's a great problem. They're telling us this time that AB is tangent to circle C. If I know it is, I'm going to go ahead and mark it. I'm just going to bank on that. What is the radius of the circle? Hold on. How am I going to solve this? This looks like a triangle where I don't have enough information. Right? I don't even have two sides. I've got like one side, and I've only got a part of the other side. Well, how in the heck am I going to be able to figure out the radius of the circle if I can't even figure out the triangle? Well, how about we go ahead and label the radius and see if that gives us any ideas. BC is a radius, right? So we just call that R. That's what we're after, right? Oh, hold on. Look at this thing. What's this guy? That's a radius too. Okay. I wonder if there's something I could do now that would help me solve for R. Could I create an equation using R? Oh, it's tangent. So that's 90 degrees. So this is a right triangle. So Pythagorean theorem works, right? Could we go ahead and try that? Let's go ahead and see if, in fact, 24 squared plus R squared, that must, if this is a right triangle, it must equal, how long is this side AC? This whole side is R plus 16, right? That's R plus 16. So this is going to equal R plus 16. And this is where you want to watch out for the classic blunder. I gave you a hint there by putting in the grouping symbols, right? All right. 24 squared gives us 576. R squared is R squared. And be careful here. What is R plus 16 squared? I'll give you a hint. It's not R squared plus 256. That's the classic blunder. Don't do it. I still like to write it out like this, even though I've been doing this for a long time. I like to write it like that so I don't accidentally forget and commit the classic blunder. So I'm going to get 576 plus R squared equals, remember, we got to FOIL this. It's just double distribution, right? R times R is R squared plus r times 16 is 16r, and plus 16r here, plus 16 times 16 is 256. Good. That was just our foiling there, if you forget. First, outer, inner, last. You get the little crescent moon, right? Okay, so, oh no, this problem has just disappointed me. Can you see how? We're not actually going to have to solve a quadratic. So, because we could subtract r squared from both sides, right? And it's gone. The r squared term is gone. 576 equals, let's go ahead and combine these like terms, right? These guys are gone, right? We'll just get rid of them. But 16r plus 16r is 32r plus 256. Okay, I'm going to go ahead and subtract 256 from both sides. And I think I get, let's see, what, 320 equals 32r. Oh no, it's turning out to be simpler than I had hoped. Oh well, 320 divided by 32 gives me 10. So what is the radius of this circle? Radius of the circle is 10. I love this problem because it pulls triangles and circles together. And the first time you look at this problem, you're like, hold on, I have no idea how to solve that. But don't forget, you can assign variables anytime you need to. And if you assign only one, you're in business. Let's try one more of these, and this would probably be a good time for you to pause the video and maybe try this one yourself, just to see how you do. They're telling us that AB is tangent to circle C. What is the radius of the circle? Okay, well, if it's tangent, I'm going to go ahead and mark that. That's an important piece of information. The only way it can be tangent is if it's perpendicular to a radius at the point of tangency. Good. They want us to find the radius. Well, BC is a radius. I'm going to label that. And then this guy here is also a radius. Okay, so what is the length of this side of the triangle? It is r plus 24, right? So now I've got a squared plus, technically it's side C. I hate to be confusing about it, but technically it's side C in this triangle. But if we're just talking Pythagorean theorem, let's say a squared plus b squared equals c squared. So we get r squared plus 36 squared equals r plus 24 squared. Good. And what is 36 squared? That's another one I don't recall. 1,296. And don't forget, don't fall for the classic blunder on those, okay? Got to FOIL that out. So we get r squared plus 1296 equals r times r is r squared. R times 24 is 24r. 24 times r is another 24r. And 24 times 24 is 576. Good. All right, well, the r squareds are going to take a hike on this one, right? And we're going to be left with, if we simplify, 1,296 equals, let's combine these like terms. We get 48r plus 576. Let's subtract 576 from both sides so that we can solve for r. And I believe we're going to be left with what, 600, is that 620? Is that right? 720, excuse me. It's a good thing I dropped back to my calculator there. 720 equals 48r. And let's go ahead and divide both sides by 48. So we end up with the radius of this circle is 15, okay? By the way, you'll notice that those are whole numbers, right? So if you happen to remember, and same thing in our last problem, if you happen to remember your Pythagorean triples, they'll come in handy. This whole side here is r plus 24. 15 plus 24 is 39. This happens to be one of our Pythagorean triples. It's a multiple of 5, 12, 13, right? If you multiply each of these sides, or if you divide each of these sides by 3, you end up with 5, 12, 13, which is one of our common Pythagorean triples. All right, new theorem, circle theorem 11. And don't forget when you're done watching this video, and maybe you want to try a little bit of the homework first, but when you're done watching this video, don't forget to watch my accompanying video where I will prove this theorem so that we can be comfortable with it. This is a really important one to remember because there's lots of free information available if you recognize this fact. It basically says that if two segments are drawn from the same exterior point, let's pick this point A, and we draw them tangent to each side of the circle, then these two segments are congruent. So if these are both tangents, you can immediately mark them and recognize them as congruent. Okay. I'll prove that in the upcoming video, the next video, but we're going to use this to solve a lot of problems that otherwise you might just scratch your head on. Let's start out with a not too hard one. Here they're telling us that AB and AD are tangent to circle C. Okay, if these guys are tangent, then if they're both tangent, both drawn from the same exterior point, then these must be congruent to one another. And you can probably see now what we've got to do. We can find an equation that would help us solve for x. If these are congruent, these expressions must be equal to one another. 6x minus 8 must equal 3x plus 7. Okay, we can go ahead and solve this for x. Let's subtract 3x from both sides. Well, we add 8 to both sides. And we're going to end up with 6x minus 3x is 3x. Cancel, cancel. Cancel, cancel. 7 plus 8 is 15. And we'll divide both sides by 3. We get x equals 5. Okay, but that wasn't the question, was it? They want us to find the length of AD. So let's go ahead and plug that in. 6 times 5 is 30 minus 8. So this is going to give us 22. Okay, before we move on to the next problem, I want you to recognize, and you'll run into some of these on the homework too, don't forget there's two theorems that we learned in this lesson. These guys are going to be congruent to one another if they're tangents. You might have to mix that in with our other theorem that we learned. You may have to occasionally draw a radius from the center to the point of tangency, and it may occasionally help you to recognize that those are right angles. And hopefully you can recall from chapter 6 when we talked about quadrilaterals, this guy is a what? If we have a quadrilateral with exactly one pair of opposite congruent angles, that's called a kite. So that may come in handy too. Don't forget that. Okay, one more of those. Maybe you want to pause the video and try this one on your own. If AB and BD are tangent to circle C, then I'm going to go ahead and recognize that those have got to be congruent. Okay, and if they're congruent, then these expressions must be equal. So in order to find BD, I can solve for x first. I'll say 2x plus 14 must equal 7x minus 11 if those tangents are congruent. And I can subtract 2x from both sides. Well, I add 11 to both sides. Cancel, cancel. 14 plus 11 is 25. 7x minus 2x is 5x. We'll divide both sides by 5. And we get 5 equals x. Okay, so how long is BD? 2 times 5 plus 14. 2 times 5 is 10 plus 14 is 24. Good. All right, let's try one more problem before we wrap it up. Oh my goodness, what's this? Okay. All right, this one is about circumscribed polygons. We finally got to circumscribed polygons. Dave is making a contemporary gingerbread house with a gable in the shape of a scalene triangle. What a rebel. He places a circular ginger snap with its center at point C so that it just touches each side of the triangle. Sounds like 3 points of tangency to me. What is the perimeter of the triangle? Okay. All right, well, this segment here is 4 inches. This side, so I do know side AB is 6 inches, but I don't know the other sides. I only know pieces of them. You know, this piece is 3 and that piece is 4. So, wonder if maybe Dave didn't give us enough information here. What do you think? The fact that these are points of tangency. You don't have to draw these radii, but maybe you want to draw them. Maybe that helps. And the fact that these are points of tangency tells me what? If this segment's 4, how long is this segment? Well, this segment's 4 as well, right? So now I can actually break down this side. If this whole side is 6 and this piece is 4, what's this piece over here? This guy's going to be the difference too, right? Well, B, we have 2 tangents drawn from this external point B, and if one of them is 2, well, the other one's got to be 2, right? And over here, if this tangent drawn from point D is 3 inches long, then this other tangent drawn from point D also has got to be 3 inches long. Okay, now do I have enough information to find our perimeter, right? If you want, you can simplify a little bit before you jump into it. You can say, well, now I know side BD is 5 inches long. And now I know side AD is 3 plus 4 is 7 inches long. So my perimeter is going to be 5 plus 6 plus 7, which is going to give you a total of 18 inches. Good. All right, guys, thanks for watching. I hope you found that video helpful. Good luck on the homework. And don't forget, check out my video that I'm going to attach to this where we prove that circle theorem 11.